Hello everyone, let's solve an interesting problem. We want to find the subtree of another tree. And not necessarily finding, we want to check if a subtree given does exist in the given root, and we want to return true if this is the case or false if otherwise. So we can see from the example given to visualize that we are given a subroot, and we know from the example case that this subroot does exist in the root given, right? If we add something like, if this child had another right child, and let's assume 3 was here, this would not count as a subroot and then will return false, because the subroot must have an exact structure in the given root. This already has a right child which the subroot doesn't, so this will equate to false. But if we wanted to return true, then the subroot must have an exact shape and structure in the root given. So I've given us some room to kind of like visualize and tackle this problem. So this problem brings to mind one that we previously solved called same tree, where we're given the root of one tree and the root of another tree, and we just wanted to return true or false if they were the same and false if they were not. And that was pretty straightforward in the sense that if the roots of the values were not the same, then we know straight up that this is false. I mean, if the give first node is not the same, then there is no how the subtrees can be the same. So that was pretty straightforward, and we just returned a false. But in this case, we know that the subtree might not occur at the root, but one of the children might be a viable subtree, right? So we want to check. The first thing we're going to do, the first step algorithm to this is just check if the first root is the same with the subroot. If it is not, then we just go ahead and traverse the length of the root given, either its left subtree or its right subtree. When we traverse the left subtree, we check, okay, is it the same with the subroot? If it's not, then we just know that, okay, this is not going to work either, and we can just continue to traverse the length of that subtree till we get to the point. As you can get using the depth first, so that's why I'm traversing one depth first before checking the other depth. So we traverse the root. If it's not the same, then we just go ahead and traverse the next node, that's the left child of the subtree. And in our case, we can see that the left child of this subtree and the subroot is the same. And if you are familiar with the tree concept, you know that every node has the ability to act as a root as long as it's a child. Every node basically can act as a root on its own. Every subtree is viable. So this can act as a root node on its own right with its own children. So as long as this form matches this subroot, we can then go ahead and compare if the children of this matches this. If it does, we go ahead and return it true because we have found a viable possibility. So the first thing is just to check, okay, the current node we are at, does it match the root of the subroot given? If it does, then we traverse the entire length of the subroot to kind of like check, because it is possible that this root matches this root, but then their children are not the same, kind of like the example we gave, where if this had another child such as this, then this will not be valid because this already has a child that this does not. So we know that these are no longer subroots. So even after checking if a root matches the subroot, we still have to traverse down that tree to check if the children or the subtrees matches. So this is going to be like a two algorithm in one, basically, where first we are checking is the root of the node of the current root node, is there anywhere where it corresponds to the subroot? If at any point it corresponds, then we can now go ahead and traverse that tree to check if it is the same tree. This is where the knowledge of the same tree that I referenced comes into play, because after we've already found a matching node, then we can now check if they are the same tree. Basically, if for instance this is 7 and this is not 4, if we check does this match, it doesn't match, then we check its left subtree, does it match, it doesn't match, we check its right subtree, doesn't match, we check all of the subtrees, basically nothing match with the subroots given, then in that instance we don't need to traverse the body of any of the subtrees because we've not found a match. Only when we find a match would we check if this entire thing matches this entire thing. And I just want to discuss the time and space complexity here and now, because it is possible that we have to traverse the entire length or the entire depth of the root given before we can find a match for our subroot. And it's also possible that we find a match, and when we do find a match, we still have to compare all of the children of the subroot with all of the given all of the possibilities in the subtree of the roots if they are a match, and the chances that we're going to traverse the entire length is the same. So our time complexity is going to be O of S times T, because basically this, or roots times subroots, R times X, that's roots times subroots basically, because we are traversing the entire length of the root and entire length of the subtree, and since we're doing this recursively, the space complexity is also the same. So let's jump right into the code. So first, let's consider our base case. What is our base case? So our base case is going to be that if our roots, if we don't have a root, right, then we're just going to go ahead and return false. And we are doing this because, okay, if we have a subroot and we don't have a root, we're returning false. Just think about it. If we have a subroot, that is the item that we want to compare with the bigger item, but we don't have the bigger item, then there is nothing to compare, and that's obviously false. So if subroot exists and root does not exist, then we're going to return false. Other base cases, like if subroot does not exist and root exists, we are going to return true, because we can bring nothing out of something. So if the bigger one exists and the smaller one called the subroot does not exist, we are going to return true. So that does not really count, because we can just use that in our functions that we're going to write. But this is the base case. This is the only time where we just want to exit the program completely, because if the bigger root does not exist, then there is no need to continue writing any function. But if it exists and others does not exist, or if both does not exist, then you can still return true, because nothing and nothing kind of like correlates, right? So if the root exists, what do we want to do? So we want to check if the roots and the subroots are the same. Then if they are the same, we want to return it true. So if the root does exist and the subroots exist, what do we want to do? We want to check if they are true. And how do we check if they are true? We check if the values are true, and we check if their left and right subtrees are true. If their values are the same, if their left subtrees are the same, if their right subtrees are the same, that is how they count as true. So we want to write a function that will check the values of the root and the subroots, its left subtree, its right subtree, and if they are true, return true. So let's go ahead and call that function is match. And because this is Python, let's initialize it using this self, and we'll just say define our is match function here. We'll call our root R and our subroot S, and we're just going to go ahead and say that. So what do we want to do here? We want to check if the value of the root is the same as the value of the subroots, and we also want to check its left subtree and the right subtree. So we'll just go in a loop here and call the function on itself and check the values of the right subtree, of the left subtree, of both the root and the subroot, and we also have to check the values of the right subtree of both the root and the subroot. Didn't spell that correctly. Okay, right dot and subroot dot right. Cool. Now what is this going to return to us? This is going to return either true or false, right? Because you know that we're using the logical operator, so it's going to return true or false. So whatever this returns to us is fine, but this would only work if root and subroot does exist, because recall that here we're only checking that the root does not exist. But it's also possible that at some point, let's say while we are traversing the tree, then one of the trees run out of values. So if the root and the subroot still exist, then we want to go ahead and run this. But if they don't exist anymore, if we have root and we don't have subroot, or we have subroot and we don't have root, we want to go ahead and compare this. And what this value is just basically saying is, because is a keyword in Python that is checking if two values are equal, this will return true if both are true. So if right is null and if subroot is null, if root is null and subroot is null, return a true. That means we're at a leaf node and this works. But if root still exists and subroot does not exist anymore, or root does not exist and subroot does not exist, then we would get a false because they do not match. So this is compressing all of that or and statements into just is keyword. So just comparing the quality of it. So recall, this is only going to check if we have both R and S. And I know this is a little bit confusing, so just to backtrack, if we have the root and the subroots, we just want to check for sure that their values and their left subtree and right subtree are the same. So I realized there might have been a bit of some background noise. I apologize. So now we've checked if a root and a subroot, if they do exist, we want to check, okay, now that you both exist, is the value and the left subtree and the right subtree a match? But if it isn't, we want to traverse the left subtree and the right subtree of the given root, because if the root itself, the given root, doesn't match, then perhaps its left subtree and its right subtree might. So we're going to call the function on itself, and we're just going to use the self is subtree. We want to pass the left subtree of the root with the given subroot, and we also want to traverse the right subtree. Root the right and against the subroots. So what is this going to give us? What is this traversal going to give us? So we are expecting a boolean, either a true or a false. So if this, when we run this, it's first going to eat this. If this condition is satisfied, it returns a false. Otherwise, it runs a function traversal on this root and subroot. So we know that it's going to return either true or false. But we are running this traversal on the left subtree and the right subtree. So we expect that one of them should return a true, right? Because that is all that really matters, that at least we have one given subtree. So we want to check if either the subtree or the right of the left side or on the right side returns a true. And we're just going to go ahead and run this. We have an invalid syntax. Okay, root the right, not right. Root the right. Let's run this one more time. We have another syntax. Okay, let's look at this more intently. This is OR. This OR is is JavaScript. Python is the literal OR. So I'm just going to check this one more time. Okay, this is another JavaScript syntax. I apologize. I was just working on JavaScript before I made this video. So triple equality doesn't work in Python. That's JavaScript. So just make this a single equality sign. And this works fine. Let's try to submit it. And this works fine too. Let's look over at our JavaScript code, which I've already written to save some time. So this is the same thing as what we did with the Python, but different syntaxes as always. So we are checking the first base case. If our subroot exists but our root does not exist, they want to return false immediately. Then we want to check the root and the subroot. If this first condition doesn't pass, then that means they both exist. So we want to check if their value exists. So we're calling this function to check if the value exists. Then we also want to check that they are both leaf nodes. That is what this line is doing. So with Python, we could use the is keyword to abstract all of these 3 lines of code, but with JavaScript we have to write it out. And then we're also traversing the entire left subtree and right subtree of the given root node to compare with the root subtree with the subroot to check if we have a subtree. The time and space complexity is the same, and I'm just going to go ahead and run this to be sure that it works. It does. Thank you so much for watching. I'll see you in the next video.